And here are the concepts of how our CubeSat would function. We envision the functionality of both our prototype CubeSat and our in-orbit CubeSat. They're very similar, but for our prototype, it's going to be held above a simulated ocean. It is going to be started via Bluetooth. And to simulate GPS, we're going to use the IMU, and it's going to be able to capture ground images and then link the simulated GPS coordinates to each of those images. And each of those images are going to be processed and hopefully identify any plastics, and then send the plastic coordinates to the laptop. And then for our system block diagram, the system block diagram displays a more in-depth step-by-step process and also the various subsystems. It shows how each subsystem is connected or interacts with the others.
This is our software architecture. From the ground station, we're gonna access our Pi through Bluetooth. And within our Pi uses PiOS, which launches and controls both the IMU and Raspberry Pi camera, which will send data to our file system. Our Raspberry Pi camera will always be on preview until it senses something and then sends the information to our file system, which we access from our Bluetooth. We're also using OpenCV, which provides a library and documentation to process our image.
Hello, everyone. My name is Angela Perez, and I worked on the mechanical layout for this project. Our team decided to begin with physical documentation rather than jumping straight into our CAD model. So what you see here is a sketch comparison between the prototype CubeSat and the in-orbit CubeSat. So the biggest difference is the camera, and it was actually the reason why we had to upscale from a 1 unit to a 6 unit, simply because the lens and the camera provided in the prototype was for short distance and wide angles, whereas we need long distance and narrow angles, which is why we were forced to upscale to 6 units. Other than that, some other differences are the GPS and ADCS for tracking purposes, and the antennas and transmitters for communication purposes.
So next up is our link budget. The link budget is an account of gains and losses in communication power between two systems. In our link budget, we have provided different calculations we have made using parameters provided to us by the course. These calculations help us understand the relationship between the ground antenna and the satellite antenna and how the amount of power between them can change when information is transmitted.
For the power budget, we figured out that the Pi, when idle, meaning that's not running any codes or being actively used, takes 2.875 watts. When it's staying at 1080p video, it uses 3.2 watts. We're not taking videos for our own demo, but it gives us a baseline on the estimated amount of power it will take to take an actual picture, since a video is just a bunch of pictures put together. When the Pi is in use to the point that the CPU load is 400%, it takes 6.4 watts. This is to know the maximum consumption of power for the Pi to make sure we can accommodate it in the event the CubeSat needs to draw on more power in space. Lastly, the camera takes 1.25 watts. Adding these together, we figured out the Pi will consume 4.125 watts when idle, 4.45 watts when taking pictures or videos, and 7.65 watts when being heavily used. The battery is really good at powering the Pi as well, as we had tested it when we left it on for an entire night, and there was some power left in the battery bank. However, for constant use, we won't be able to generate enough power for the Pi, since the solar panel given to us only provides 2.4 watts when facing the sun, which is not even enough to power the Pi when it's in idle.
So next up is our mass budget and bill of materials. And basically what this is it's just a list of all of the items that are going into our CubeSat, the cost or estimated cost, the mass, and the quantity. So some examples of the things we have on here are the Raspberry Pi, which costs $45 and weighs 46 grams. The the camera, which costs $29.95 and weighs 3.4 grams, and the SD card, which costs $19.95 and weighs around 2 grams. And here is a continued list of our mass budget and bill of materials. So some examples of the things that are on here are the acrylic panels, which cost around $2.50 and weigh about 14.5 grams. And the half-inch nylon standoffs, which cost around 86 cents each and weigh about 0.4 grams. And the totals, so we added everything up, and the totals that we found are that the cost would be $153 with 56 cents, and the mass would be 119.6 grams.
So for the data budget, we figured out that the Pi memory had 2 gigabytes of RAM. However, there was only less than 1 gigabyte available. And with each photo being 4 megabytes each and the Pi having 1 gigabyte of RAM, we divided the two and we calculated that it would be approximately able to hold 250 photos.
So the Raspberry Pi is equipped with a high-quality 8-megapixel camera board, which features a fixed focus lens, and it's capable of taking 3,280 by 2,464 pixel static images. And its horizontal field of view is 62.2 degrees, while its vertical field of view is 48.8 degrees.
So for our integration and test plan, the question in hand was how would we be able to combine everything that we've done in order to test our flight? And with the bill of materials, we decided that we need a Raspberry Pi camera, a blue tarp, and a 2mm by 4mm colored object. To set up for the testing, we ping the Raspberry Pi with Bluetooth, and the CubeSat would be placed 1 meter in height above the tarp, and the 2 by 4mm object would be placed on the tarp. The photo would be taken via Bluetooth, and then with the photos being taken, we'd process the pixels of that photo in order to identify debris and the colored objects within those photos. The ADCS is the equivalent of IMU in this case in our prototype, and we'd capture IMU data in order to simulate what would help us receive GPS coordinates to identify where the debris exactly is. And we'd combine the IMU data to the photo that was taken, and the vision processing would be done through OpenCV, which we would filter colored images to look for the debris of a distinct color. If there is debris that was identified, we'd save that photo. And this process would be repeated as we go through the tarp, because the Raspberry Pi would not be a still object in space. When the CubeSat reaches the downlink region of the tarp, so where it is able to send its data down, we'd send the selected pixels and the coordinates of the debris.